Okay, welcome to this lecture on basic surveying, and today we are in module 9, lecture number 4. This is our entire schedule plan, the way we are proceeding in this video lecture. So right now we are in computation and adjustment. What we have done so far in our last lecture, we talked about adjustment by observation equation method. We saw what is the meaning of the observation equation, how we frame that, how we include the parameters as well as the observations in the adjustment process, and the adjustment is being carried out by least square technique. So we saw the basic derivation for this and as well as some examples. Finally, I also gave the procedure, how to apply it, the steps. Now today in this lecture we are going to talk about same adjustment, but we are going to talk about the adjustment by condition equation method. So what we will do today, the condition equation method, we will go for the basic derivation, then again we will see some examples, and finally the procedure. Well, in the case of the condition equation method, we know now that why we carry out the adjustment, because we have the observations from the field. Observations have got the redundancy. Always we have something which is desired, which we want to compute finally from these observations. So in this process, those desired quantities, for example shape of a triangle, can be determined by some minimum number of observations, but we are taking more number of observations. And if you are taking more number of observations, there are various ways in which the desired quantity can be computed. So what we are looking for? We are looking for the best possible way, which is the least square technique. So in our adjustment process, we are making use of the geometric conditions, which we say the functional model, and as well as the quality of the observations, which we take into account the quality of the observations by weight matrix or the stochastic model. Now in the condition equation method, what we will do? Well, the conditions include only observation. This is important. Unlike observation equation method, where we are including the observations as well as the parameters, the unknowns, here we include, or rather we write the conditions using only observations. So we should keep this in mind. Then second, there will be as many conditions as the redundancy in model. So C is number of the equations which we are going to write, and R is the redundancy. We know R is n minus n naught, that is R, where n naught is the minimum number of observations which can define our desired thing. N is actual number of observations. Now the conditions we will write of the form, that's the general form here. As you can see here, if I highlight that, is the general form. LA stands for adjusted observations. So basically we are writing our conditions of this form. In terms of adjusted observations, LA will be writing the conditions. Now LA, which is adjusted observation, is LB is observed, something which we are observing in the field, and V is the residual, because finally our estimate, because LA is our final estimate, the adjusted observation. This is actually something which is observed in the field. We know this which is observed in the field has some error. So what we are saying, error means the correction. In something which we observed in the field, we are applying this correction, and by applying this correction we get LA, that means the estimate or adjusted observation. So what I can do, I can write it as function of LB plus V is equal to 0, and finally this can be written as a function of variable, the residuals. V stands here for residuals, is equal to F. So we will be trying to write our equations or conditions finally in this form. Now how we will do it, this is what we are going to see now. And this form Fv is equal to F is our functional model. Somewhere in the process of adjustment, we will also include our stochastic model. Well, let's do it for one case. Okay, right now it is that we have n number of observations, and for that particular problem, n naught is the number of observation which can define the problem, or which can find the answer for us. The desired quantity can be determined by only n naught. So number of observations are n, minimum needed n naught, the redundancy in our model is r, which is n minus n naught. So obviously we are going to write r number of condition equations. Now how we write this? A general form. It's a general form. We are writing the equations in the form of, we'll start with number 1 here. You can see, please notice here, V1, V2, V3 and so on, Vn. What is the meaning of this? There are n number of observations. Because there are n number of observations, so each observation will have its residual. So we have the residuals from V1 to Vn. And as we saw, we want to write our model of this form. Okay, or also I can write this model as A, V is F, where A is a matrix of coefficients, V is a matrix of residuals, F is a matrix of constants. So this is how I want to write my final model. Well, the same I am trying to do here. Now A11, A12, A1n, these are the coefficients, and F1 is the constant part. Then, because we have to write r number of such equations, so we are writing, this is the rth equation. Now if these equations, we write them in matrix form, so we get our first matrix here, which is of coefficients A11, A12, A1n, A21 and so on up to ARn. So this matrix A is of size Rn. Then we have a matrix for V, the residuals, which is of size N1, and these are the coefficients R1. Once we look at one example, then it becomes more clear what we are trying to do. But this is the general form. So we are starting to learn it from the general form. So our general form, we can write our basic functional model as AV is equal to F. And how we are arriving at this? We arrive at that from FLA is equal to 0. From there only. What is the meaning? From here we are arriving at this. The meaning is, first of all, we are looking for the conditions in our system. How many conditions are there? We are looking for those independent conditions. R number of conditions will be there. Ensure that those conditions should be independent. Once we have found those conditions, then for those conditions we are writing the equation in the form FLA is equal to 0 in this form. So basically, condition number 1, one set of equations, second, third, fourth, depending how many, what is the redundancy, the total number of equations which are required. Now once we are writing these equations using the conditions, FLA here stands for estimate or the adjusted observation. So once we are writing the equations that way, we are writing those conditions in terms of, this is important here, we are writing the conditions in terms of estimates. That's why FLA, this is important, is equal to 0. This is our starting point. And then, because we know LA is LB plus V, observation plus the residual, so we are putting in that condition equation or the condition which we have just written, LB plus V, and then we expand it. And from there, we get our final model of the form AV is equal to F, where V, as we have seen, is a matrix of residuals, A is a matrix of coefficients, and F is a matrix of constants. Well, Once we have formed this basic model, now what we want to do? In this, A and F are known, and we have to determine the V. If we can determine V, we can determine the parameters, because the parameters, as we know, LA, we are writing LA is LB plus V. LB we know, V we will know after adjustment, so we can determine LA. So our job here is to find V, the residuals. Now how do we find it? We make use of the principle of least square, and the principle of least square says, over here I am also including the stochastic model. So principle of least square says that V transpose WV should be minimum, isn't it? So this is what we'll try to do now, but there is a problem here. The problem in this case is we have only R number of equations, while number of unknowns are n. Number of the residuals are n. N is number of the observations. For each observation, the residual is there. And R is smaller than n. So we are in a situation where we have more number of unknowns than the available equations. So how to solve it? What we will do, if we go for the least square, then in this least square we cannot substitute for each V or each residual, because we have less number of equations. Because what we will be doing, as we did in the observation equation method. In observation equation method, we had sufficient number of equations, and for each V we substituted its value from the equations that we had formed, and then we put those in the least square solution, and the rest of the solution follows. But here in this case, because we have less number of condition equations, more number of unknowns, so we cannot substitute for V in our least square solution. So what to do? Well, in this case we know we will like to go for a constrained minimum. It's not a free minimum as in case of observation equation method. So this constrained minimum will get those constraints again by where from the conditions which we have. Well, we will see this by an example, this entire process, because so far we are looking at the general case. In general case, starting from FLA is equal to 0, the conditions written in basic adjusted observations or the estimates. These are the basic conditions which we are writing. Then we are we are replacing this LA by LB plus V, and then we are forming our model of the form AV is equal to F. Alright, then we need the least square solution. Now we have seen just now that the least square solution is not possible directly, rather we have to go for constraint minimum. How to do that? This process we are going to see now by one example, because it will be easier to understand this in the example. Well, the example in our case is again the one which we have taken in our previous classes or the previous lectures. What is the example? We are starting from a benchmark and going to a point x1. Okay, the benchmark is known, this RL is known, and this is a point for which we want to determine the RL. What we are doing, by labeling, we are determining the difference in elevation. Similarly, we have another point x2, x3. So what the job is, we want to determine RL of x1, x2 and x3, as we have done over here. Now in this slide, x1, point number 1, point number 2, point number 3, and their RLs are x1, x2 and x3. Now in order to determine these RLs, we have seen the minimum number of observations that we need to carry out is we need to observe L1, L3 and L5, only 3. So by taking 3 observations, this problem can be solved. But this solution will be a unique solution, no redundancy. So actually what we do, we rather go for more observations. So how the observations have been taken here, starting from benchmark, we have reached point number 1 by observing L1. Then from point number 1, find the difference between point number 2 and point number 1, which is L2. Again, starting from benchmark, we have gone to point number 2. So we found the difference between benchmark and point number 2, which is L3. Again from benchmark, we have reached point number 3 by finding the difference between these two heights or their heights, which is L5. So L5 is the difference in height between point number 3 and the benchmark. Again, from point number 2, we walk to point number 3 and found the difference between these two heights, which is L4. So what we have done, we have taken 5 number of observations. So the redundancy in this case is 5 minus 3 is 2. So if we have redundancy of 2, we will need to write 2 equations here. Now what these 2 equations will be? So we are writing the 2 equations, and as we know, the equations should be of the form, the starting point is f LA is 0. This is the form of the equation in adjusted observations. Now observations here are L1, L2, L3, L4 and L5. These are the actual observations which we represent as LB, and the adjusted one or the estimates we write as L1 hat, L2 hat, L3 hat, L4 hat and L5 hat, which is LA. Well, in terms of these adjusted observations, now we will try to write the conditions. Now, can we see some condition over here? If you follow the arrow, you start from this point, you go to x1, point number 1, point number 2 and go back to benchmark again. So basically what we are doing, you are finding the difference between these 2 points L1, difference between point number 1 and point number 2 L2, and point number 2 and point number 3. So we are starting from a point, going to this place, coming again here and then going back. So if you are finding these differences in elevation, and if I add those differences in elevations, their sum should be 0, because we are starting from a point and we are reaching the same point again. So their sum should be 0. So this is how we can form the conditions. Well, the first condition over here, the very first condition is along this road L1 plus L2 minus L3, because the sign is important here. The L3 has been observed in this direction, so that's why I am using minus L3. So that's our first condition. How about the second one? Well, the second is again in another loop, starting from L3. Let us do it with some other color. Yes, starting from L3 plus L4 minus L5. So L3, L4 minus L5. This is the second condition. So this is what we were saying is of the form f LA is 0. Now we have written our basic conditions. Now we know that L hat is L plus V, and this is what we are going to replace, or otherwise also we are writing as, so we are going to replace now in place of L hat L plus V. So we are going to replace this in these two equations. Well, let us do it. So these are the basic two condition equations of this form. By replacing means, for L1 hat you write L1 plus V1, L2 hat is L2 plus V2, minus L3 hat is L3 and V3. So because minus sign here, so minus L3 minus V3, this equal to 0. Similarly, L3 plus V3 for L3 here, L4 hat, L4 plus V4 minus L5 hat minus L5 minus V5, this is equal to 0. So basically in place of LA we have replaced it by LB plus V. This is what we have done now. Now what we are doing, we are rearranging it. Now just rearrange, because we know finally we want to reach in this format, okay, as we saw in our general case also. So by rearranging it, bringing all the V terms on left hand side, so V1, V2 minus V3, V1, V2 minus V3 is equal to, you are taking L1, L2 and L3 on the right hand side. So this is minus L1 minus L2 plus L3. And mind it, all these three are known. Why? Because these are the observations. This is something which we observed in the field. So we write these three as a constant F1. Similarly, for the second equation, V3 plus V4 minus V5. V3, V4 minus V5 is again another constant here. Now this equation, which we have just written over there, we are rearranging it. So in rearranging to include all observations. In the general form, we had written, V1 to Vn, all were included. So we are trying to do the same thing over here. So it is V1, V2 minus V3, V1 coefficient is 1, 1, minus 1. There is no term of V4 and V5 here. So 0, 0 coefficients and F1. So I'm just trying to rearrange it. Similarly over here. Well, all these are the coefficients which are written in blue here, and they will form my matrix A. So if I write it in the matrix form, the matrix A becomes 1, 1, minus 1, 0, 0. So 1, 1, minus 1, 0, 0, and 0, 0, 1, 1, minus 1, 0, 0, 1, 1, minus 1. So that's my matrix A. And the V matrix is V1 to V5, and this is the coefficients, the F1 and F2. So what we have been able to do, we have been able to generate or write our basic conditions in this form. Well, next is the step which we left there also. We said now we want to go for the least square. In order to go to the least square, we would like to have, number one, the stochastic model with the quality of the observation. So we'll talk about that, and then how this problem can be solved by least square, because the problem here is we have more number of unknowns than the equations. So we are going for the constraint solution. Well, about the stochastic model, for each observation L1, L2, L3, L4, L5, we have some weight. We know how to assign these weights, the quality of the observation. So the weight matrix for uncorrelated observation is this, a diagonal matrix. Well, about the solution, because that's the least square and we want to minimize this for the least square solution, V transpose W V, and if I expand this, it is W1 V1 is square, W2 V2 is square, W3 V3 square, W4 V4 is square, W5 V5 is square, and this sum should be minimum. Now again this same problem which we were talking earlier, that we cannot replace for V's here, because if I want to replace for V1 and V2, V3, that's not possible, because the way our condition equations are, if you look at our basic condition equations here, these equations from here, I can, because we have only two equations, so we cannot replace for V1, V2, V3 in our this phi which we want to make minimum. So how we are going for the constraint minimum now? So we will be making use of Lagrange multiplier in order to solve this. Well, our conditions, what I am doing now, instead of phi, earlier we were using phi, we are introducing now phi dash. Phi dash is nothing but same phi, that's phi, plus in addition we have now two more terms. One term is minus 2k1 V1 plus V2 minus V3 minus F1. I will explain how it is coming here. And minus 2k2 V3 plus V4 minus V5 and F2. Now where from these are coming? If you look at this carefully, it is V1 plus V2 minus V3 minus F1. This is nothing but our first condition equation. The condition equations which we had formed is this: V1 plus V2 minus V3 is a constant F1. Okay. So what I have done in this condition equation only, the condition equation number 1, I have taken this F1 on the left hand side and I have replaced it here. Well, that's the very first condition. And this is the second condition here. This is the second condition. Now, so what we have done, instead of phi, I have introduced the phi dash by introducing these two new terms. Well, if my observations are adjusted, or if we have determined V1 to V5, we know them, and we know them for adjusted observations, then in that case this V1 plus V2 minus V3 minus F1, this should be equal to 0. For the adjusted observations, this should be equal to 0. Similarly, here also this value should be also equal to 0. V3 plus V4 minus V5 minus F2, this should be also equal to 0. So because this particular term is 0 and this term is also 0, both these terms are 0 for adjusted observations. So including these two terms, first here and the second here, in this phi dash, it doesn't have any effect actually, because for the adjusted observations, or we can say the other way around, if phi dash is minimum, that is equivalent to say that phi is also minimum, because for adjusted observation this term and this term is already 0. So what we will try to do, because we know now that if we are saying that minimum of phi dash corresponds to minimum of phi for the adjusted residuals. So instead of minimizing phi, we will try to minimize phi dash. Well, why we are writing here 2k1 and 2k2? These are the Lagrange multipliers, and the value 2k1 and 2k2 because it helps later on in the solution. We could have written lambda 1, lambda 2 also. Well, now we have taken a decision. Well, we are going to minimize phi dash. So if you are going to minimize phi dash, how to solve for that? We know we will be finding the partial derivatives of phi with each of these variables V1, V2, V3, and we will be equating that to 0. Well, let us do it. If I do it with respect to, let us say, V1, if we partially differentiate this with V1, what we get? Del phi dash del V1 is, how many terms of V1 are there? One term is this, so 2 W1 V1, no term here, no term here, and then one more term over here, which is minus 2k1 V1. So minus 2k1. So the first partial derivative, against this variable V1 is 2W1 V1 minus 2k1. So we write it here, 2W1 V1 minus 2k1. Similarly, with respect to this variable V2, V3, V4 and V5, and we are equating them all to 0, because this is what we need to do in order to minimize phi dash. Well, once we have equated them to 0, next we can from these find the value of V1, V2, V3. For example, here the V1 will be 2k1 divided by 2w1. So V1 will be 1 by w1 into k1. Alright. Similarly, we can do it from here for the V2 also. and for V3, for V4, for V5. So the V5 will be minus K2 divided by W5. So we are going to write these for V1, V2 and others. So V1 is K1 by W1 K1, V2 is 1 by W2 K1, and this is for V3 1 by W3 minus K1 plus K2, V4 is 1 by W4 K2, and V5 is 1 by W5 K2. Next, we will be now rearranging these terms. The same thing, this I am writing now in this slide here. Now in rearranging it, how do we rearrange? V1, V2, V3, V4, V5 in matrix form, we are writing it here, because all these equal to K1 by W1. Look at you see the way I have written over here. I have written the W terms separately here. W1 by W1, 1 by W2, 1 by W3, 1 by W4, 1 by W5. And all of these I am putting here in a diagonal matrix. Then the terms for, see, we have K1 and K2 here, and then the coefficients. So K1 and K2, the coefficients of K1 and K2 over here. For example, in the very first one, the coefficient of K1 is 1 and K2 is 0. So I am writing 1 and 0. Similarly, over here in the second one, again 1 and 0. For K1 it is 1, for K2 it is 0, 1 and 0. Now in this equation, it is minus 1 and plus 1. So minus 1 and plus 1. And similarly, over here, 0 for K1, 1 for K2, 0 and 1. And over here, 0 and minus 1, 0 and minus 1. So what we have done, we have rearranged these equations in matrix form. Now this is very significant, this is important. We will make an important observation here. Now what is that observation? This is V, capital V, we see the residual matrix, and 1 by W1, 1 by W2, 1 by W3, 1 by W4, 1 by W5. This is inverse of weight matrix. Inverse of weight matrix is theta, we represent it by theta, which is called a cofactor matrix. And this is K matrix, we say. Well, this is important here. What is this? If you look back, when we were forming the equations, now here, this matrix is A. If you find A transpose, you get the matrix which you have just seen. This is A transpose. So how we can write it? We can write it, this is V, cofactor matrix, A transpose and K. So we are writing it now as V is theta, A transpose, K. Now over here in this, we know that AV is F. We know it because this is how we had formed our initial equations. AV is equal to F. Now in this, we are replacing this V by theta A transpose K. So this is what we are doing. A and this is V. Theta A transpose K is equal to F. Well, from here, can we found K? So to find K, we will take A theta A transpose on right hand side. So we find K is A theta A transpose inverse F. Well, if we write the same thing again here, K K is A theta A transpose inverse F. Now in this, what all is known to us? Well, F is known to us because F is a matrix of constants. Now where from these constants came? You remember when we are forming the equations, we took all the observations, something which we had observed on the right hand side. As well as sometimes, for example, in a triangle, the sum of three angles is 180. That is also a constant part. That is already on the right hand side. So all the observations have gone to the right hand side, and those, they form the F. So we know this F, the constant part. How about A? A is also known because A, the way we form the equations, A is a matrix of the coefficients of residuals. So A is also known to us. And how about theta? Cofactor matrix, which is inverse of weight matrix. Yes, this is also known to us because this means the quality of the observations, the stochastic model. So over here we know all F, A and theta. So if we know them, we can determine the value for K. So the K matrix can be determined. Over here K1 and K2. So these are known to us. Now once we know K1 and K2, we know, because we had arrived earlier at V is theta A transpose K, and the K is known to us now. If K is known to us, A is known, theta is known, we can also find V. So we can find V because by theta A transpose K. K is already determined, A is known, theta is known, so V is also determined. Well, if the V is determined, what next? The LA is LB plus V. Because V, the residuals are known, we will add these residuals in our observations and we can find the adjusted observations. So finally, we are able to determine the adjusted observations. So in this process, what we did is starting from our basic conditions, we could now find the adjusted observations, or we say the estimates of the observations. Once we had these adjusted observations in this particular problem, L1, L2, L3, L4, or we can say, we know now L1 hat, L2 hat, L3 hat, L4 hat, L5 hat. All these are known to us now. If these are known to us, I can simply find the value of x1 as benchmark plus L1 hat. Now whichever way I find, whichever route I take, I can find this x1 by different routes in that network of the level. I will get the same value of x1, and this is the x1 is my parameter, the unknown, the desired quantity which you wanted to determine by these observations. So this is the procedure of adjustment by condition equation method. Okay, now the general form. The general form is, I'm going to give you the procedure how to solve the problem by adjustment by condition equation method. Well, in this, first of all, in that particular problem, whichever is the problem, look for the number of the observations. What is the minimum number of observations which can define the problem? Then find the redundancy and how many unknowns are there. First of all, write the conditions of this form, and these conditions once you replace for LA as LB plus V and rearrange the term. So you need to form our functional model of this form. So this is the functional model which we have arrived from here. That's the very first step. So the important thing is to look in that particular problem, where are the independent conditions, and those independent conditions should be equal to the redundancy, and we have to write those condition equations. This is very important, starting of the problem, the very first step. We have to look at the problem. We are solving here for the simple problems, but sometimes the problems could be very complex. Still we have to find, well, where are the conditions, and we need to write those conditions in this form. F LA is equal to 0, and then replacing this LA by LB plus V, finally we need to write it in this form. So over here R is the redundancy, N is number of observation. Once we have done it this way, we need to compute for K, the K term. We know now where from this K term is coming, and we know it is A theta A transpose inverse F. That's the K. Once this K is known, we can find, because the K is known, A theta A is also known, theta is also known, we can find the V. And once the V is known, we can also find the LA. And our problem is solved. So this is a general procedure which we have to adopt. What we'll do now, we'll take one example, a very simple example but interesting example. The example is, we have a line, we are taking the observations of the length, okay, and we are taking multiple observations. Let us say we have measured this line 3 times. If we have measured the line 3 times, these observations are, first observation is 10 meter, second is 13 meter, third is 12 meter. Okay, this is possible, 3 observations. What is desired here? The desired is L hat. L hat means what is the length of this line? What is the estimated length of this line? That's the desired. So N naught, if you are looking for the N naught means we are writing at 1. No. What is the minimum number of observations which are required in order to find the answer here? Well, 1 observation. You measure the line once, you have the estimate of the line, or rather you have the, if that observation is true observation, you have the true value of the line. So basically we need only 1 observation. But we are taking 3 observations because in 1 observations we don't have any check on the error. So we are taking 3 observations here. So redundancy in our case is 2. Now we know we will be writing the number of the equations equal to redundancy. So we need to write 2 condition equations here. So where are the condition equations here? This is what we need to see now. The conditions. And the conditions are to be written in terms of adjusted observations. The observations are L1, L2, L3, and the adjusted observations will be L1 hat, L2 hat, L3 hat. These are the adjusted observations. So we need to write the conditions in terms of these adjusted observations. Fine. If this is adjusted observation for the line, for the length which we are talking about, and this is also the adjusted observations. Of course, both are adjusted. Both the observations have been adjusted. That means both should be same. So this is why we are writing the first condition equation. L1 hat minus L2 hat is equal to 0. Similarly, the second one we can write as L2 hat minus L3 hat is equal to 0. So these are the only 2 possible independent conditions which we can write here. And this is important. The very first step of writing the conditions is very important. We are writing here because L1 hat minus L2 hat is equal to 0. Because both the observations are adjusted. If they are adjusted, these should be same. Well, having written it, next step we know we need to replace for L hat as L plus V. This is what we are going to do now. Okay. If you replace, so L1 hat is L1 plus V1 minus L2 hat minus L2 minus V2 is equal to 0. This is L2 hat minus L3 hat. Okay. Now minus L3 hat over here, please check, this should be minus, this is not plus, this is minus. Well, having done that, we want to rearrange these terms. In rearranging means we want to keep, because finally we want to write it in form of AV is F. So we are taking all the constants on right hand side. We are putting the V terms, the residual terms on the left hand side. So I take the residual V1 minus V2. So V1 minus V2 is L2 minus L1 is equal to 3, because L2 is 13, L1 is 10. So L2 minus L1 is 3. So V1 minus V2 is equal to 3. Similarly, V2 minus V3, V2 minus V3 is equal to minus 1, because V2 is, this is L means L2 minus L3, that means 12 minus 13 is L3 minus L2. L2 is 13 and this is 12, that's why it is minus 1. Now, in AV is equal to F, in this V, we need to bring all the V terms, V1, V2 and V3 in all the equations. So what we are doing, we are bringing them here, and I am writing the coefficients also. So 1 into V1 minus 1 into V2 and 0 into V3. This is the equation which I am writing here again by rearranging, by bringing all V1, V2 and V3 equal to 3. Similarly here, no term of V1 here, so 0 into V1, 1 into V2, minus 1 here, so minus 1 into V3 is equal to minus 1. Once we have written it in this form, now we will write it in the matrix form. So in the matrix form, as A, V is equal to F, you can make this A from these coefficients, because we know the A is the matrix of coefficients. 1 minus 1 0, 1 minus 1 0, 0 1 minus 1 0, 1 minus 1, and V is V1, V2 and V3. This is equal to 3 and minus 1. So what we have been able to do right now, we have been able to write it in this form, AV is equal to F. Now we need to look for, at this stage, the stochastic model. Means, what is the weight matrix? If we know about the weight of these observations, we will consider those. Over here, we are considering the weight to be same, the identity matrix. So all the weights are same, all the observations have been taken with same precision. So this is, so the weight matrix is identity here. Well, if we know that weight matrix is identity, so we are going to find the solution. How do we find the solution? We have already seen the general form. This is where we have written the general form. After knowing A, theta and F, I can find K, and once we know K, we can find for V. So this is what we are doing here now. We know A, we know F, so the K can be determined now. K is A transpose inverse F. Let us do it, and then we will find, once we know the K, we will find V. So K is A transpose inverse and F. So we can solve it now. If you multiply these two, we get 2 minus 1 minus 1, 2, because inverse, so inverse of this F matrix here. Then again further, the inverse of this, you can determine this is here, and this is the F. So the K, finally we can solve it, comes out to be 5 by 3 and 1 by 3. Okay, so we know K. Once we know K, we can, using V is A transpose K, because this weight matrix is identity, so I am not including the theta term here. So once we know K, we also know F, we can find V. So V is A transpose K, where A transpose is written over here and this is K. So by solving for this V can be computed. Please do these computations for this particular problem and other problems also. So this is what is V. Now what these V's are? These are the, because then a basic model. What was our basic model? LA is LB plus V. Means we have determined the V. If we add these V to observations LB, we will find LAs, means L hats. So L1 hat can be computed by L1 plus V1, and this particular value is 11.66. Similarly, for L2 also, L2 hat can be computed by L2, the observation. This is plus V2 means minus 1.33, and this is also 11.66. Similarly, L3 also, L3 hat can be computed because this is L3 minus, the plus V3. What is V3? Is minus 0.33. So again 11.66. So what we observe here, L hat, something which was desired is 11.66, as well as we are observing the L1 hat, L2 hat and L3 hat are now same. And this is what is our basic assumption. All these three adjusted observations have to be same finally. Something which we observed in the field. In each observation, the amount of the error is different. That is why the three observations are different. But we know that our adjusted observations should be same. And this is how we wrote the conditions, our two conditions here. And by this procedure of adjustment, the way we have done just now, what we saw that finally we get for each observation, we are getting the corresponding residual or the correction. So by applying that correction to that observation, we are getting the estimate of that observation, or we can say adjusted observation. So L1 hat, L2 hat and L3 hat, these are three adjusted observations for observations number 1, 2 and 3. And as we thought, assumed earlier, or as our condition was earlier, these three are same. Okay, so this is what we have done by this particular exercise. We have now found the desired thing. The desired thing was length of the line. Okay, the estimate of the length of the line, which we have found as 11.66 by following the procedure, so that all our observations were, we included all the observations and followed the condition equation method and adjusted the observations. One interesting thing, we have proved this before also. Generally what we do when we have the observations like this, for one line we have three observations, and what we do without realizing the concept of adjustment or the least square approach, what we do, we take these three observations and find the arithmetic mean. And we had proved also, when we are talking about this adjustment, that arithmetic mean is also the least square solution. Okay, is the best estimate. We have proved that also earlier. So over here also, if I do the same thing, the arithmetic mean is L1 first observation, L2 and L3 divided by 3. So this particular value also comes out to be the same. So this also again we are proving here. What we found from the least square adjustment is same as the arithmetic mean. So what we have seen in this lecture, in this video lecture, we saw the condition equation method. How do we start from the beginning? We have to look into the problem, where the conditions are. We have to see how many observations have been taken, what minimum number of observations are required in order to define the problem, find the redundancy. Once the redundancy is known, then we write equal number of conditions. So we have to look into the problem, that where these conditions are. So after writing those conditions, and this is really the important step, the most important step, we replace, because we are writing the conditions in terms of estimates. So we replace those estimates by observation and the residual. And then we write finally in the form of AV is equal to F. And next, once we have written this, we include a stochastic model, the quality of the observations. And then rest of the solution is simpler, it's very, very simple. Just we have to do some matrix manipulation and finally we get the V. V is the residual values. Once we have the V, we can find the adjusted observations and then finally the parameters, something which was desired. So this is what we discussed in this lecture. Thank you.